Assalamu alaikum wa rahmatullahi wa barakatuh. So we are still talking about the design of absorption column, and we are trying to estimate or determine the diameter of the column. Keep in mind the determination of the diameter is based basically on avoiding flooding, which basically it has nothing to do with mass transfer rate. For this part, I will be using the same reference like last one, which is basically principles and modern application of mass transfer operations by Jamie Bennett's chapter 4, which is available in the bookstore. In this video and the next one, we will be talking about tray tower and the determination of the diameter of a tray tower. As a reminder, which basically the operation of a tray tower is basically the fluid or the liquid is passing from the top to the bottom. So the liquid is passing from the top to the bottom and then cross flow through the tray, get accumulated by the weir, and then flowing down directed by the downcomer and in the other direction and so on. The gas is passing from the bottom to the top through the holes and then through the liquid, where they would have the intimate contact with the liquid phase and hopefully separation before, hopefully mass transfer will take place before the separation of the gas and the liquid. Now remember, we are always trying to avoid flooding. At the same time, we need to make sure we don't have any weeping. So again, as a reminder, weeping is basically liquid is going through the holes, and flooding is basically liquid cannot flow downward. So basically, if we have high gas flow rate and maybe even liquid, high liquid flow rate, so with the high gas flow rate, the liquid will not be able to pass through the downcomer, and it will start to accumulate until it reaches the second tray, the third tray, and eventually get outside through the gas pipeline. So basically, when the downcomer is filled with liquid, it's basically a flooding situation. Now, the design constraint for the design of the tray tower in terms of diameter, it's all based on fluid dynamics. We need to make sure that we don't have flooding, otherwise the process basically will be unusable and we will have to shut down. We need to make sure that we don't have excessive entrainment, too much liquid is carried out by the gas upward. We need to make sure that we don't have any weeping, which is basically liquid is passing through the holes. And obviously we need to make sure that we don't have any dumping. Dumping is a worst case compared to weeping, where all the liquid is passing through the holes. Nothing is basically going over the weir and through the downcomer area. So the idea is basically to operate within this envelope, within this design constraint. And basically we will have flooding if we have high gas flow rate, high liquid flow rate. We can have weeping if we have low gas rate and high liquid flow rate. Dumping, obviously low gas flow rate, low liquid flow rate, and at high gas flow rate with small amount of liquid flow rate, then we will have excessive entrainment. With an increase of liquid flow rate, we can have flooding. So again, as a case of reminder in terms of design constraint, in chapter 3 we were saying that in an absorption process, in order to decrease the number of stages, we need to increase the solvent flow rate. So by decreasing the number of stages, we will reduce the overall height of the column. However, as a design constraint, if we keep increasing the liquid flow rate, it's true that the column will be smaller, it will be shorter. However, we might reach flooding point, we might reach weeping point. So as a design constraint for increasing liquid flow rate, is going to be the flooding point, the weeping point, and obviously on top of that the pressure drop. In general, for every tray, the maximum allowable pressure drop should not exceed 1.2 kilopascal per tray. In some references, they consider 1 kilopascal per tray is the maximum allowable pressure drop per tray. So we have design constraints, many design constraints, but we always have to keep in mind flooding, weeping, and pressure drop. We should never cross those lines, and to control that we need to control the liquid flow rate and to control the gas flow rate. This is why the determination of the diameter of the column is mainly based on in fluid mechanics. It's not based on mass transfer rate. So to determine the tower diameter in a tray tower, we start with determination of the flooding velocity. So this equation is very similar to CS flood in packed column. If you remember CS, so instead of CS here they are using capital C. So we calculate the flooding velocity by determining capital C and density of liquid, density of the gas. We will see later on how we can calculate capital C. And once we determine the flooding velocity, we can easily determine the diameter with the same concept that volumetric flow rate of the gas will be equal to pi over 4 the cross-sectional area multiplied by the flooding velocity by the velocity. So the velocity of the gas will be basically flooding velocity multiplied by the approach to the flooding velocity, 50%, 60%, 70%, and so on. So it depends on the approach to flooding. Now the only different thing is basically when we were in a packed bed, we were saying that the cross-sectional area equal to pi over 4 diameter squared, diameter of the column. However, in this case here, we know that the gas does not pass through the whole column. If you remember in the downcomer section, downcomer area, that section in the tray is not perforated, and therefore gas will not be passing through the downcomer area. It will pass through only the remaining area, which is the active area and the open area for the downcomer. So we need to calculate what's called the net area. So the net cross-sectional area, AN, which is 1 minus AD over AT. AD is the total or the overall cross-sectional area of the tower by over 4D square, and the area taken up by the downcomer, which is called here the downcomer area. So once we know the flooding velocity, we can easily calculate the diameter of the tower by using volumetric flow rate equal to cross-sectional area multiplied by the velocity of the gas, which can be calculated by specifying the approach to flooding, 70% or 50% or whatever. Now this term AD over AT, downcomer area over the total area, can be estimated by considering the value of capital X. If you remember, capital X was L prime over V prime, density of the gas over density of the liquid to the power of 0.5. So if X is less than 0.1, then AD over AT will be equal to 0.1. If it is more than 1, then AD over AT will be equal to 0.2. And if it is in between, it's going to be this value here. So now we know everything except the value of capital C, which is basically an empirical value which can be calculated using this equation, FST, FF, FHA, CF. So all of these are factors added together in order to calculate capital C. So FST is basically the surface tension factor, which is calculated using the liquid surface tension in dyne per centimeter. FHA or FF is the foaming factor, which is basically the tendency of the fluid to foam. So the higher the tendency, the lower the foaming factor. So if you have non-foaming liquid, foaming factor will be equal to 1. For many for many solvents is equal to 0.75 or even less. If we are using water as the solvent, the foaming factor can be considered to be equal to 0.9. So this is FF. Next one is FHA. And FHA is the factor relating the ratio of whole area to tray active area. We already know what is the active area, which is the bubble area on a tray. And the whole area is basically the summation area of all the holes on that tray. And basically we can determine the value of AH over AA by considering the arrangement of the holes on those trays. This arrangement will have different arrangement. They can be like this one here, which is equilateral triangular arrangement, or it can be square arrangement, or it can be diamond shape arrangement, and so on. So this is the most common one, and basically the diameter of a single hole will be equal to d naught, and the distance between the centers of two adjacent holes will be p prime, which is called pitch value. This is very similar to the design of shell and tube heat exchanger, where the arrangement of the tubes will have different arrangement, and they will have specific pitch value for the space between the tubes. So we have this P prime and we have D naught, and the ratio of a whole area over active area. Remember, whole area is the total area of all of these holes. So the ratio of whole area over active area can be calculated using the diameter of a single hole over pitch value, P prime. So once we calculate this, the ratio, we need to check if it is more than 0.1 or less than 0.1. If it is more than 0.1, the ratio, then the factor is going to be equal to 1. If it is less than 0.1, then the factor will be calculated using this equation. Now, this is something that we will see later on during the example, but it will always helpful to determine what is the length of the weir and what is the distance of the weir from the center of the tray. And in order to know that, we need the sine theta, the angle theta. So if we determine theta, we can easily calculate LW, the length of the weir, and RW, the distance of the weir from the center of the tray. Keep in mind, this is LW, the length of the weir. It's not the height of the weir, it's the length of the weir. And we can calculate theta by determining AD over AT. Remember, we already know AD over AT from the previous slide as a function of x. So we can solve for the value of theta, then we can calculate LW and RW if we know what is the diameter of the column. We will see the application of this in the example. So now we know FHA, the remaining is CF. And CF is a function of capital X and alpha and beta. Alpha and beta, they are a function of T, which is the tray spacing, the spacing between the columns, between the trays. And in order to determine this tray spacing, there is basically different schools in determining the tray spacing. For example, in the US, they say tray spacing is always equal to 0.6. Or some companies in the US, they say tray spacing is always equal to 0.6 meter. In some companies in the UK, they say tray spacing can be 1 foot, 2 feet, 3 feet. So 12 inches, 24 inches, and 36 inches. And this is basically standard values. You don't go somewhere in between. All right. However, there are some guidelines for the tray spacing. So recommended tray spacing based on the tower diameter. If it is less than 1 meter, then the trace spacing will be equal to 0.5. Between 1.3, the trace spacing is 0.6. That if the diameter is between 3 and 4, the trace spacing is 0.75. And this is where we see some of the companies, they are saying trace spacing is always equal to 0.6, because usually the tower diameter is between 1 and 3 meters. Usually, not always. So the thing here is, in order to know the trace spacing, I need to know the diameter. And actually, I need the trace spacing in order to know CF, in order to calculate C, in order to know the diameter. So basically, it's a matter of trial and error. We need to assume diameter, tower diameter, determine what is the spacing, calculate CF, calculate capital C, then calculate the flooding velocity, then calculate the diameter. If we have the same diameter as our assumption, then our assumption was correct. If not, then we will have to repeat with a different assumption of the diameter. Now, I need to bring to your attention this statement here, which is basically, in order to calculate CF, we need capital X, logarithmic value of 1 over X. So to make sure that we have a value for CF, if X is less than 0.1, we have to shift or force the value of X to be equal to 0.1. Because less than 0.1, then we will have a negative value for, unknown value for CF. So if we have capital X less than 0.1, in that case, I have to force the value of X to be equal to 0.1. If it is more than 0.1, then I should use whatever value I have. So that's it. I now know FST, I know FF, I know FHA, I know CF, I can calculate capital C. Once I calculate capital C and knowing the densities, I can calculate the flooding velocity, and then I can calculate the diameter straightforward. So let's apply this in an example, which is basically the same example we had for in a packed bed. It's the same ammonia absorber with the same conditions, and we would like to see how is the design of a tray tower will look like for the same conditions. We need to consider a foaming factor of 0.9, and we have a liquid surface tension of 0.9 per centimeter. We have the hole diameter of 5 millimeter, pitch value of 15 millimeter, and the sheet metal thickness is 2 millimeter. So from the previous example, we know the value of capital X, density of the gas, density of the liquid, and volumetric flow rate of the gas. We know we can determine the ratio of downcomer area over the total area by knowing capital X. Capital X is 0.9, so it is less than 0.1, so AD over AT will be equal to 0.1. Next, we need to calculate capital C. So we need to determine FST, which is the surface tension. We just need to substitute sigma with 70 dyne per centimeter, and FST will be 1.284. Next, we need to determine FF, foaming factor, which is given in the problem statement, FF equal to 0.9. Next is FHA. For FHA, I need to determine what's the value of the ratio of AH over AA, which is a function of hole diameter and the pitch value, and therefore AH over AA is equal to 0.1, and if it is equal to 0.1 or greater, then FHA is equal to 1. Last thing is CF, and for CF I already have the capital of X, the value of capital X. I need alpha and beta, and for alpha and beta I need to estimate or guess the value of trace spacing. From the previous example, we calculated the diameter to be less than 1 meter. So my guess is I'm going to assume that the diameter is going to be less than 1 meter. So trace spacing will be equal to 0.5 meter. Knowing the trace spacing, now I can easily calculate alpha and beta, and then I calculate capital CF will be equal to 0.079. Now I have the value of the 4 factors. I can calculate capital C. I forgot to mention that if you remember, x value equal to 0.092, and since it is less than 0.1, I have to force it to be 0.1. So in here, I put the value of capital X equal to 0.1, not 0.09. So now we calculated the value of CF, calculated the total value of capital C. Now I need to go and calculate the flooding velocity. I know the density of liquid, density of gas, capital C. So the flooding velocity is equal to 1.329 meter per second. Then I can easily just calculate the diameter using this equation. I know everything. The approach, in the previous example, the approach to flooding was 70%. AD over AT equal to 0.1. I know the volumetric flow rate of the gas stream, so the diameter equal to 0.32 meter. So now as you see, the diameter of the tray tower equal to 0.32 meter. From our experience, we must not have a tray tower with a diameter less than 0.6, because it will be very tight for a person to get inside and install the trays if the diameter is only 0.32 meter. Now, this is our tray. We have the downcomer area. If you remember, there are no holes. We have the holes inside or in the bubble area. We have the weir, and then we have the downcomer area. So basically what we know now, we know the total area equal to of a tray equal to 0.08 meter square. Downcomer area is equal to 0.008 meter square meter. We know the active area, the bubble area, will be the total area minus one downcomer here, one downcomer from this side, so it's equal to 0.064. We know the whole area, the area of all the holes here, which is 0.1 of the active area. So this is the value of AH. Now what's remaining is what is LW, the length of the weir. Remember, this is not the height of the weir, it's the length of the weir. And RW, which is the distance of the weir from the center of the tray. And to know that, we need to know the angle theta that is connecting the weir to the center. And once we know the theta, we know theta is related to AD over AT. So AD over AT equal to 0.1, already determined. So we can solve for theta, which is in radians. And once I know theta, I already know the diameter, which is 0.32 meter. I can easily calculate LW and RW, which I did here, and LW equal to 0.268 meter, and RW is 0.172 meter. And by this, basically, we have a complete design of the tray. We know the areas of the area of all sections of the tray. We know the diameter of the column. We know the hole size. We know the distance between two holes. We know the length of the weir. We know how far the weir is from the center. And we know the thickness of the tray, which is 2 millimeter thick.